Thank you for that introduction, and thanks for the invitation. I think it's an honor to come back here and be able to come here and be able to talk to you about who I am and where I came from and what I do. And I want to thank everyone that was involved with organizing this. It was obviously a monumental effort, and people devoted a lot of time to that, and I really appreciate that. And thank you very much for the introduction. Okay, so I want to tell you a little bit about who I am. I'm a professional astronomer. So I get paid to study the stars. I have one of the most useless jobs on the planet. I don't make anything. I don't sell anything. I don't advise. I don't counsel. I don't recommend. And I don't judge. I don't have anything to do with anything that has any practical relevance to anyone's daily life. And yet, consider this. When I'm on an airplane, which I am a lot, and this person next to me tries to strike up a conversation, if I feel like talking, if I don't feel like talking to them, I'll tell them I'm a physicist. But if I feel like talking to them, I'll tell them I'm an astronomer. And we are fascinated, as a people, we are fascinated by astronomy. The second most common thing that the person sitting next to me will ask me, or will say to me is, I really wanted to be an astronomer when I was a kid, but... and then some excuse follows for why they didn't end up becoming astronomers. So I'll come back to that but, which I think is quite important. But my point remains, which is that we are fascinated by astronomy. It's in our souls. I am fascinated by astronomy. It's a part of my soul. So why is that? Well, partly I think it's because astronomy deals with extremes, the biggest, the densest, the oldest, the astronomical. Partly it's because astronomy deals with things that are so foreign to our daily lives, black holes, neutron stars, the Big Bang, exotica. It's fascinating. But mostly I think it's because we all want to know and need to know the answers to those questions, those big questions. And you all know the big questions I'm talking about. Where did we come from? How did we get here? How long will we last? And of course, the big question, are we alone? Is there other life in the universe? We all want to know the answers to these questions, and we need to know the answers to these questions. It's some foundational part of us. And I need to know the answers to these questions. I want to know. And that's why I'm a professional astronomer. So I want to tell you how I got to be lucky enough, and I am very lucky, how I got to be lucky enough to actually get paid to try to answer these questions. So I grew up, fairly typical small town in the middle of America, pretty close to middle America. So the town is called Stunton. It's a small town in south central Illinois, not too far away from St. Louis, but really not something you would call a suburb in any way, shape, or form. It's located in a county, Macoupin County. You may never have heard of it before. So it's an otherwise sort of nondescript square county. It's not of many communities, rural farming communities mostly. Most of which, none of which are actually bigger than 10,000 people, or a little bit over 10,000 people. Stunton itself, so there's the Wikipedia page, the extremely short Wikipedia page on Macoupin County. It tells you right there that there's 50,000 people as of the 2000 census in the entire county, which is a fairly large county. The primary industry is agriculture. So again, your typical Midwestern town. Stunton itself is, like I said, not too far from St. Louis. It's a quintessential small Midwest farming community. It has about 5,000 people. It has quite a few churches and bars, fewer stoplights, of course, the whole town is centered around the main drag, which, you guessed it, Main Street. It's an old mining community actually, and is now again mostly farming. The biggest employer in the town is the school. And the people that live in Stunton embody those traits that in many ways, I think, personally feel characterize Midwesterners. Hardworking, unpretentious, uncomplicated, more concerned with friends and family than prestige or some sort of external measure of success. Just genuine, honest, real people. Not a very large town at all. So in fact, I didn't even live in this very small town. I actually lived several miles north around some lake in very rural Illinois. So part of it, I'm showing this because my parents are in the audience and they'll appreciate showing the small house that we used to live in out in the outer community. So so Stunton is, again, just very, very typical of Midwestern, small town Midwestern communities. There is one school, and the school is split into an elementary building and a high school building. So graduating from junior high to high school meant traversing a hallway from one building to another. And of course, football was king. I was one of those kids, the kids Max just told you about, right? I was always asking questions, always happy to share my newfound knowledge with anyone who cared to listen or didn't care to listen. In fact, I have to apologize. I want to take this opportunity to apologize to everyone who was subjected to me as a child, especially my parents, and particularly my parents. I was definitely an inquisitive kid. And it's this inquisitiveness, this drive, this unceasing drive to learn, to understand, that's exactly what eventually drove me to become a scientist. I personally believe that all of us have this drive. Right? The difference between people like me who eventually go on to become professional scientists and those people on the plane who say that they wish that they would have become an astronomer, right, is that in my case, this inquisitiveness was nurtured, and in their case, the inquisitiveness was suppressed somewhere along the way. And so I was fortunate enough that I had people in my life that encouraged this inquisitiveness and nurtured it and really fostered it and made me to stick with it. And so first and foremost, of course, I want to thank these people. And so I want to take this opportunity to talk less about myself and more about the people that actually were responsible for making sure that this inquisitiveness burned bright in me. So particularly my parents. So this is my family. This is me quite a while ago. I've changed a little bit. There's my sister, Tana, and there are my parents, who I'm very lucky to have. They came up here, and they're in the audience today. And I want to thank them. The countless sacrifices that they made in order that I could be successful. I also want to thank my grandfather, who was also very instrumental in keeping this inquisitiveness alive. We spent hours in the basement of his house in his wood shop just talking about anything. He's showing me whatever he could. He used to sit me on his lap and show me the stars, something I actually did not remember, but he reminded me of not that long ago. Certainly something that must have been important for me eventually becoming an astronomer. But so how did I actually end up finding my true passion, my true profession, which is astronomy, studying the stars? So for that, I have to thank one other of those people that have really fueled my drive to learn. And that's my second grade teacher, Mrs. Eleanor Gregory. Eleanor. So I had no idea she had a first name. I'm just shocked. And again, I'm very lucky that she made the trip up here from Stunton Elementary, where she still teaches 42 years later. Still teaches second grade. She was my second grade teacher. And she was the first person to really teach me science. And my mom likes to say that she spent an entire year teaching just me science, which is probably true. So one day, one day she gave our class an assignment, which was to go and to look up the name of the 9 planets. So there were 9 then, names of the 9 planets, right? And memorize them in order, the names of the 9 planets in order. And so, you know, things have changed now. But so I went home, and my parents had gotten a subscription to National Geographic. And at the time, with National Geographic, the subscription, you got 3 sort of picture atlases. One of them was called Our 50 States, which talked about all of our 50 states, obviously. One was Our World, talked about all the different countries and you know, populations and everything. And one of them was called, is this book right here. It's not this book that we had, but it's the same book, Our Universe. And in it, it's basically a brief history of astronomy in words and in pictures. And so I pulled this book off the shelf, and I cracked it open. And you know, in this book, there's, like I said, a brief history of astronomy. There's everything from stories about Newton and his apple and how he came to realize that the gravity that holds the moon is the same thing that causes things to fall on the earth. Something that also stuck with me, the density of Saturn. If you had a bathtub big enough, if you put Saturn in it, it would float. Something very hard to forget. But what really struck me in this book, there was a whole section on the idea of what life might be like on other planets or other bodies in the solar system. So there was just fantastical creatures, big blimp-like creatures floating in Jupiter because, of course, there's no surface on Jupiter, or creatures that fed off of pure radiation skating on the icy surface of Jupiter's planet Europa, or oucher-poucher type creatures that fed off of metal and rock in Venus, or cold crystals creatures that lived in the frigid temperatures of Pluto, or hydrocarbon burning creatures in Titan, creatures with enormous ears, bird-like creatures in Mars. I was just fascinated by this idea. Of course, all of this is just ridiculous, right? I mean, there aren't these creatures living in these bodies on these worlds, but the idea that this kind of life could exist elsewhere, I was just hooked, and I knew that this is what I had to do. This was my calling. So that was really what really struck me, and I really and kept with me and made me realize that at that point I just had to be an astronomer. My course was set. So I have to thank Mrs. Gregory for that assignment. It changed my life. And of course, there's one more chapter. There's many important chapters in my life, but there's one more chapter that was absolutely critical. And of course, that's the reason why we're all here, and that's IMSA. In a town where football is king, I'm not sure what would have happened to me if I had finished high school in Stunton. I'm sure I would have been successful. I doubt I would have been anywhere close to this successful. One day, someone came to our school in Stunton. I was a freshman in my freshman physics class in Stunton, Joe Edel from the charter class. And he came and he told me about this magical place, literally magical place. And sitting there listening to him talk about classes and residential life and learning, pure learning, it was like heaven. So I applied, and I was accepted. And so I went to IMSA. Traveled that 4 hours north from that small town in Staunton to join the residential life at IMSA. It's hard to explain how profound of an effect going to IMSA had on me. It permanently, most importantly, it had many effects on me. It changed me as a person. But most importantly, it cemented my desire to learn. And it gave me the knowledge that it was my absolute right to learn at all times throughout my life, and that no one has the right or can take that away from me. And that is kept with me and is really critical for my future success. And the rest, as they say, is history. I spent 3 amazing years at IMSA, and I won't say it was all good. It wasn't. I had some hard times at IMSA. There are several people in the audience today, Eric McLaren being one of them, that I would like to thank in particular for helping me through some of those hard times. But looking back, although they were horrible crises at the time, looking back, they were fairly normal growing pains for a teenager. So I made it. I graduated from IMSA in '91. And after that, I went to Michigan State University, majoring in astrophysics. From the first day, I signed up as an astrophysics major and stuck to that. I got my Bachelor's of Science in Astrophysics in 1995. And then I went to graduate school at Ohio State, getting my PhD in 2000. And eventually coming back as a faculty member at Ohio State University. I still remember the day that I got my first paycheck as a graduate student at Ohio State. So I was paid a stipend. Very small stipend, I would have you know, but I was paid a stipend to go to graduate school at Ohio State. And I stared at that check literally for a couple minutes because I just could not believe that someone was actually paying me to do what I loved. So I am truly very lucky. Okay, so I was asked to talk about me. That's enough about me. What I really want to talk to about is I really want to come back to the quest for those answers that we all want to know. And so I said the second most common thing that I get from the person sitting next to me from the plane, the second most common thing that they say is, I wanted to be an astronomer. Of course, you probably can guess what the most common thing they say. And the most common thing that they ask me after they find out that I'm an astronomer is they say, do you think there's life out there? Are we alone? And of course, I always answer, being a scientist at heart, I don't know. They hate that. And then they usually say, yeah, but what do you think? And then I say, I don't know. I say, but I'm trying to figure it out. And so unfortunately, right now, it's hard to just answer that question scientifically. Are we alone? Is there life out there? We're not quite there yet, although what I want to show you is that we're actually remarkably close. So instead of asking that question and trying to answer that question head on, we can ask a series of other questions that are a little bit simpler and things that we can answer today. So things like, are there other planetary systems out there? Do those systems happen to look like our own? How common are solar systems like ours throughout the galaxy? How common are planets like ours, third rock from the sun, Earth-like planets with water and clouds and life? How common are those? And do those planets have life? Right? Those are the questions that we can hope to answer first, eventually getting to that question, are we alone? So I want to give you a little backstory here, which you may or may not be familiar with. Before 1995, this was the one planetary system that we knew of around a normal star. That's, of course, ours. And again, there were 9 planets then, only 8 now. So our planetary system is actually quite interesting. If you were to go out and design a planetary system, it might not be the first planetary system that you would design. So, if you like uniformity, you might have all the planets be the same size. Or if you like some sense of order, you might have the biggest planet next to the sun and then they slowly decreasing like sets of nested dolls as you go further out. But not at all. That's not how our solar system looks. We have sort of 3 sets of planets. We have 2 giant planets, 2 medium-sized planets, and then 4 little puny balls of rock. And these planets are not sort of scattered randomly throughout our solar system. We have the small rocky planets that are located very close to the sun. And then we have the giant planets that are spaced ever-increasing distance from the sun. The biggest planet, of course, being Jupiter, sitting about 5 times the distance of the Earth from the sun. And these planets, the giant planets further out, they're made up of big balls of gas, hardly any rock. Whereas, of course, the inner solar system is made up of big rocks. So why does our solar system look like this? Why does it have this sort of peculiar architecture? Why these different classes of planets? Well, we have a theory, and we had a very well-developed theory. When we had one planetary system, of course, the theorist went crazy and came up with a perfect explanation for exactly why our solar system must look like that. And it goes something like this, right? Very simply. So it turns out that we think our planets are basically the leftover dregs of star formation. So when our sun formed, it's formed from a big ball of gas. And that big ball of gas was too heavy for its own weight. It collapsed under its own weight. And the very densest part of that ball of gas eventually got dense enough to start fusing hydrogen and helium and became our sun. But there was some gas left over, and that gas left over formed a disk that orbited the sun. And then in that disk, there was gas, and there was also little bits of dust. And this dust, small dust like what you'd find underneath your bed, slowly settled to the middle of the disk and there started to stick together. And eventually, these little dust particles became the size of pebbles and then boulders. And once they became the size of sort of large cars, then they can start attracting each other gravitationally. And then those things come together quite quickly and form planets. So that explains why all of our planets are in a disk, and all inclined and all going in the same direction about the sun. But why is it that we have the big planets further out and the little planets close in? Well, as you get farther away from the sun, it gets colder. It's pretty obvious. And so the stuff that you make planets out of when you're closer to the sun is going to have stuff that is hotter than the stuff that's further away from the sun, is colder. And eventually, if you get cold enough, as everyone knows, it begins to snow. So at some point, when you get far enough away from the star, you can have ices. And when you have ices, then you just have a bunch of stuff to make planets out of. And so at some point, some magical point, about 3 times the distance of the Earth from the sun, this disk began to have snow in it. And there's a lot more snow than rock. And so this snow, this ice, came together to form planets very rapidly. And eventually you got to a planet that's big enough that it can actually start to hold on to gas. Right? And so at that point you form a Jupiter and a Saturn and a Neptune and Uranus. Inside to that snow line, the place where it snows, you just don't have enough stuff to grab onto gas. And so what you end up with are rocky, mostly dry planets with not a lot of water on them, like the Earth and Venus and Mars. And so that's the theory that we have come up with, very simply, for why the solar system looks the way it does. Too hot for ice, cold enough for ice. So inside you form rocks, outside you form icy gas giant planets. And that explains our solar system. So that's all well and good. Right? It's nice to have a theory that explains something that you already know exists. But of course, when the first planets were found around other stars, well, the story just wasn't so nice. So the first planet was found around another star in 1995, around a star 51 Pegasi, who before that no one had ever heard of. It's a star before that only its mother loved. But once this planet was found around the star 51 Pegasi, the 51st brightest star in the constellation Pegasus, this planet was found by two gentlemen pictured here, Mayor and Queloz, Michel Mayor and Didier Queloz from Geneva Observatory. They found a wobble in the star. They saw that the star was moving back and forth along our line of sight, which indicated it was being orbited by a massive planet, a planet about the mass of Jupiter. Right? And so it's a star similar to our own, 40 light years away. Again, otherwise nondescript star that no one cared about beforehand. Now, that's pretty exciting to find a planet around another star. It's obviously a huge step forward in this field. But what was really surprising about this planet is where it was located. Right? So I'm showing here the inner solar system. So there's Mercury, there's Venus, there's Earth. So Mercury, of course, is the closest planet to the Sun, and it's very close to the Sun, about 0.4 times the distance of the Sun, of the Earth from the Sun. This planet around 51 Pegasi, it's located about 10 times the radius of its star from its parent star. It is sitting right up against its parent star. There you see a cartoon of what this planet might see. Right? If you were actually standing on the surface of the planet, this star would actually take up about 30% of the sky. That's how big it is. Right? Completely unexpected. These giant planets are only supposed to be located in the outer part of the solar system where our Jupiter is, and yet this giant planet, this Jupiter-mass planet, is located far interior to any of the planets in our solar system. And to say the least, this threw the astronomical world on its ear. Many people didn't believe it was it was actually a planet, but it turns out it is. We have conclusive evidence of that now. And since then, we've found a bunch of strange new worlds. About 350 of planets are known around other stars. And this plot shows that their orbits look like if you were looking down on them. And then there's Jupiter's orbit. So most of these planets are located well interior to the position of Jupiter from the Sun. Again, completely unexpected. And not at all consistent with this theory that I just outlined for you for how these planets should be formed. And so we just don't understand how planets form. It's an open question. And unfortunately, most of the methods that have been used to find planets are only sensitive to these very close-in planets. We don't know if there are planets like our own solar system out there, Jupiter and Saturn. And we really have no idea whether or not there's Earths, which is really what we want to find out. That's because most of these methods, as I mentioned, are not sensitive to these planets. So what do we know about systems like our own, the ones we're really ultimately interested in? Well, most techniques, like I said, cannot detect Jupiter and Saturn, our giant planets in our solar system. But one technique is, and this is the technique I work on. It's called gravitational microlensing. This technique was actually predicted by Einstein, but famously, one of Einstein's very few blunders, I think, he predicted that it would never be observed, that this effect of gravitational microlensing would never be observed. Well, he was dead wrong. Again, one of the few times that Einstein was dead wrong. The way this method works, it's quite interesting. It really works like a gravitational lens. So you have some star, some source star, which I'm showing in this plot to the left, that's actually emitting light, sending light in your direction, and you're observing it with your observatory. Well, if you have some other star, this lens star that I show, that passes between you and the line of sight to this more distant star, it acts like a magnifying glass, magnifying this background star. And so what you see is this background star gets brighter and fainter over time. But if that foreground star, that lens star, has a planet, well, that planet will act like a magnifying glass as well. And so in this figure on the right, I'm actually showing actual data of a star that you can see get brighter and dimmer. And in one short period of time, it gets much brighter, and that's when the planet is actually magnifying this background star. And so you can use this technique to find planets. And the exciting thing is you can find planets that are at the separations from their parent star, like our Jupiter and Saturn. We spent a long time developing this method. I spent my entire graduate school career working on this method, not finding any planets. We found a few now, and I want to share with you one discovery of what we found last year. Last year, we found 2 planets using this technique, orbiting one star. And these 2 planets have properties that are very similar to our Jupiter and Saturn. So here's an artist's conception of these 2 planets orbiting this distant star very far away from us. Here are the physical properties of this. You don't have to read this, but let me just tell you what they are. The star itself is about half the mass of our sun. It's about 5,000 light years from the Earth, so it's quite far away. The star is about half the mass of the sun. The planet is pretty close to the mass of Jupiter. The separation of one planet from the star is about half the distance of Jupiter from the sun. And then the separation of the other planet is about half the distance of Saturn from the sun. And it's also close to this mass of Saturn. So you see this similarity here. Half the mass of the star, of the sun is this mass of the star, half the distance between Jupiter and the sun, half the distance between Saturn and the sun. It's as if you took our solar system and you just shrunk it down. You scaled it down to another solar system. And that's what we found. And it's the first analog to our solar system that we found around another star. And what's exciting about this is that you can use this detection, right, to ask how common are these solar systems. And the fact that we found this one system, even though we haven't been looking for very long, we've only found 8 other planets using this technique, suggests that these Jupiter-Saturn analogs, plus solar systems with a Jupiter and a Saturn, are probably not rare. They're probably quite reasonably common in our galaxy. And who knows, the solar system could actually be a complete analog to our solar system. There could be Earths closer into than the giant planets. There could be Uranus and Neptune's further out. We wouldn't know because we wouldn't have detected them, but it could very well be an analog to our solar system. So this is pretty exciting. We're actually reaching that point where we're being able to say how common are solar systems like our own. So we're working our way down that list of questions that I mentioned, right? And we're getting there even today. But of course, really what we want to find is we want to find things like Earth, right? And you might think that this is something very far in the future, but it's not. There's a satellite mission called Kepler. And Kepler is going to find planets in a completely different way, which is extremely easy to understand. It's going to wait for the planet to pass in front of the star. And it's going to use this very, very complicated property of the planet that you can't see through it. And so that when the planet passes in front of the star, it will block some of the light from this parent star, create a shadow on the star, which you can measure by measuring how bright the star is. That's as complicated as this method is. But you need to go to space to do it because the signals are extremely low, extremely small signals. So Kepler is a mission that will go out and it will be sensitive to Earth's at the separation of Earth. It will be sensitive to Earth analogs and will learn how frequent these Earth analogs are. And this mission, like I said, will detect Earth-like planets if they exist. Mission launches tomorrow at around 11 o'clock p.m., right? If all holds. So cross your fingers, right? This will be a revolution in astronomy, finding this. Of course, eventually, really what we want to do is we want to search for life in the universe. And if you thought finding Earth was a long way off, right, you might think that finding life is just ridiculous. It's never going to happen in your lifetime. But that's not so. Of course, what we want to find is we want to find a picture that looks like this. Does anyone know what this picture is? Shout it out if you do. Nope. Any other guesses? Nope. I'll give you a clue, though. That is a picture of the Earth. Right? This is a famous picture called the pale blue dot picture, taken by the Voyager satellite as it was exiting the solar system. Carl Sagan convinced them to turn the Voyager around and point back towards the solar system and take a picture of these tiny pinpoints of light that were the planets. So every single human being that was alive at the time when this picture was taken is located in that little pinpoint of light, which is no bigger than 1 pixel. Right? It is not even resolved in this picture. That is what we're looking for, is these pale blue dots orbiting other stars. But with this pale blue dot, which you think maybe you can't learn anything from, you can learn an enormous amount. You can actually take the light from this pale blue dot, you can divide it up into its component wavelengths, take a spectrum of it, and you can look for the signature of oxygen, which we think was entirely created by life on the Earth. You can look for the signature of methane, which is created by some single-celled organisms like methanogens, and of course, also created by cows. I love to show the picture of a cow, right? So just with this picture of a pale blue dot, you can learn an enormous amount, right? And again, you might think that we're a long way away from this, but we're not. The future is basically now, or very soon. The missions are being built. All of the technology we need to do this is available today. We can do it, right? There are challenges to be overcome, but they're not fundamental challenges. So missions are being built or planned that will allow us to detect and characterize these pale blue dots and take the light from these pale blue dots and look for oxygen, look for methane, look for the signs of life. And these missions could have results in the next few decades, or maybe if you're pessimistic in the next 50 years. So maybe not in my lifetime, I'm optimistic. I think in my lifetime it'll happen. But if not in my lifetime, then the next generation. So we are privileged. We live in a privileged time when we are actually beginning to answer these questions. And in the very near future, for the first time in human history, in the very near future, we can actually expect to answer this question, not, philosophically, not with Hollywood screenplays, right? But with actual scientifically answer this question, are we alone? And so we're in a very privileged time. I consider myself amazingly lucky to be part of this story, to be able to go out and find planets and be able to answer these questions. And I consider myself also very lucky because I have these people that really helped me throughout my entire life and made sure that this flame of inquisitiveness was not extinguished. And I had IMSA to go to that really cemented that inquisitiveness. Thank you very much. Oh, yeah, sure. I'll take as many questions now.
That was spectacular. Oh my goodness. Scott, thank you so much. What a great story, and I just can't, my head's ready to explode just thinking about all this. Really fantastic. We have time for a few questions before we go back upstairs. Scott, I'm going to turn this over to you.
Oh, sure. Yeah.
I know that your focus is extrasolar planets,
Sure.
but isn't there indications that there could be life in our solar system? What with Europa, I believe, being filled with water and recent revelations with respect to possible water on Mars?
Yeah. Excellent question. Unfortunately, I just didn't have time to touch on that. It might be, so I teach a course in astrobiology, which is a field that no one would have admitted to actually working in 10 years ago, but now is actually a burgeoning field that actually gets funded. And it's because of this progress. So in this course, I spend a full third of it on the prospects for life in the solar system. And some of the best places that we think are quite hopeful are Europa, for example. And so a number of things have come together with Europa that makes it quite exciting. So indeed, yes, we think it probably has a subsurface ocean beneath this ice layer. And the reason why it has this ocean is it's being squeezed by Jupiter, which causes it to be hot on the inside. And so we can imagine that there might be hydrothermal vents at the bottom of this ocean in Europa. Now, what's interesting about that, right, is that if we go and look at hydrothermal vents on the Earth, right, in the very bottom of the ocean, no sunlight gets anywhere close to these vents. And the temperatures are actually above the boiling point of water at atmospheric pressure, but down there at those pressures, it's still liquid, obviously. We find that those vents are teeming with life. And not only that, we can genetically code that life, and we find that it is ancient. And not only that, not only is this ancient life that's extremophiles, hydrothermophiles, they love the heat. Not only is it ancient, if we actually map the tree of life genetically, it all points back to these heat-loving organisms. So it might very well be that this is where life originated on the Earth, which makes the prospects for Europa extraordinarily exciting. Right? And Mars, of course, yes, Mars we know had liquid water. We know now, and this again, very recent revelations, we know had liquid water in the past. I was just talking to someone actually before my talk. It could very well be that we're all Martians. It could have been that life arose on Mars first, microbial life, that then got blasted off of Mars, ended up landing on the Earth and seeded life on the Earth. I think that's a fascinating possibility, and it is a realistic possibility.
Mm-hmm. And has a lot to involve with astrophysics. Where does astrology stand in all this?
So astrology is not a science. I guess it's a belief system, just like in a religion of a sort, I guess I would say. So I approach life as a scientist, and what people do and those kind of areas is their own business. I want to learn the answers from empirical evidence. This is not the way astrology works.
One more?
You talked about the search for life being looking for Earth-like planets, but if you go all the way back to your book when you were a kid, I mean, would there be life on other types of life on other that live in other mediums or
right.
ways, not organic?
Yeah, well, it's an excellent question. So, for example, life on Earth is all carbon-based, and it all requires liquid water. People have asked whether or not we could actually use silicon. So you go next down on the periodic table and you find that silicon has very similar properties to carbon. And maybe you could use alcohol as a solvent instead of water. People explore that. It's hard. Carbon works well and water works well, and so it seems like it's a natural thing. But the real answer to your question, of course, is we just have no idea. And so if you're trying to find something and you don't know what you're looking for, it's really hard to design a mission or a scientific plan to go look for anything, right? So what we do is we pick something that we know worked on this planet, right? And we use that to guide what we're looking for. And then, we try to keep our mind open to other possibilities. So it's just more out of practicality than anything else.
One more, Mike.
For what percentage of the time that the Earth has been in existence,
Mm-hmm.
has there been life on Earth? And so, for instance, if you find a planet that's like ours, what's the likelihood that life could be there or was there and is no longer there?
It's an excellent question. So it somewhat depends on what you call life, but we have fossil evidence for life dating back. So the Earth is about 4.5 billion years old. We have fossil evidence for life dating back over 3 billion years ago, and that's firm fossil evidence for life. We have less conclusive but very suggestive evidence for life about 3.8 billion years ago. That's a very interesting number because it is thought that the last sterilizing impact on the Earth, so the last time that the Earth got smacked by something that wiped out all life on the Earth, happened between 3.8 and 4.2 billion years ago. So all evidence that we have is that life arose on the Earth as soon as it was possible. And in fact, may even have arisen before and got wiped out and started again. So that's single-celled organisms. So that suggests that single-celled organisms are very robust. As interesting is that complex life took another several billion years to evolve. And so multicellular organisms took a long time. And of course, we arrived on the scene yesterday in cosmic time. So it might very well be that simple life is robust and happens easily as long as you have conditions that are remotely good for it to arise. But that complex life requires a series of unlucky or special circumstances in order for it to happen. Or it could just take longer. I don't know. I think that people have fierce debates about this. So I don't know if that actually answers your question, but it's the best I can give you.
All right. Scott, I'm going to take one more minute. The lights were down, so we did not have the opportunity to meet some key folks. So I would like to ask your parents. Is it Eleanor, your second grade teacher?
Eleanor.
Your parents, Eleanor, Dr. McLaren, Dr. Marshall, others who knew Scott at Dr. Marshall, Dr. McLaren as well. Thank you. Well, Scott, on behalf of all of us, we are so grateful that you have kept that sense of wonder and curiosity and have shared that with us in such an articulate fashion. And it's the kind of thing that I know this weekend I'll be able to tell Trent a little more. And I think we'll all be able to go and share these stories with those with whom we work. And I hope that as Eleanor, as your parents, as Dr. McLaren, Dr. Marshall, your RCs at IMSA touch your life, that we can go and do the same for others. And it was just a terrific inspiration, and thank you so very, very much.
Thank you.